Awesome. Well, thank you for being with me here today. My name is Natalia Varela. I'm a PhD student at Virginia Tech, part of the Sedimentary Systems Research Group led by Brian Rumans. And I'm going to be talking about turbidity currents, which are kind of associated with these processes happening in Antarctica as part of IODP Expedition 374. So the motivation for this work was one of the questions of, what kind of other processes can trigger turbidity flows, but without the sediment being the main driver, and already has been touched upon in this seminar, which is kind of oceanographic processes that are more related to differences between like density due to temperature and salinity. So this is where we're interested in. So the process itself that we are interested in is actually what happens in the Southern Ocean, precisely in the Rouse Sea in Antarctica, where the formation of bottom water is related to the formation of these areas known as polynyas, which is our ice-free areas that being created by the push of very strong winds that come from the ice sheet. So the kind of free of ice, these areas where then again the new sea ice is being formed, and every time that that happens, it kind of left behind this very dense and very silent water, and this process is known as brine rejection. And this water, this very dense water, kind of sinks down and create this turbulence, this convection down deep into like the shelf area. This water kind of goes either downslope along current flows, but also can create these very large plumes in the area that goes from the continental shelf to the continental slope, bringing not only more like cold waters, but also some sediment transport. Now the plume itself can reach up certain height, right? That can give us this the possibility, of course, that the sediment kind of flows up enough just to like reach out beyond the boundaries of the channel and being deposited on the areas of the levee, as we see here in this plume, in this process called flow stripping. Yeah, so the point is that all this process is leaving behind a record of what we're going to be looking into, for example, shown here by this orange arrow. Now, this process in itself doesn't really happen everywhere. As I mentioned before, this happening mostly in the Southern Ocean during winter time. And this process also, of course, is related to the formation of this bottom water, the Antarctic bottom water, which in turn is connected to the formation of dense shelf water. So as probably you already know, that the Antarctic bottom water is very important in the entire conveyor belt. It's the coldest and deepest water mass in the ocean. And there are like three main sites in Antarctica where we can see this bottom water formation, which are the Weddell Sea, the Rouse Sea, and the Adelie Coast, as shown by these arrows over here. Another thing that is important is that this formation is like recent. I mean, these points are still active, and in these areas are very vulnerable to the changes in climate, as we all know, especially in the area of West Antarctica where the Rouse Sea is located. So bottom water formation here is shown by this diagram where like these sites were drilled by Expedition 374, and we're going to especially concentrate in site 1524, marked here by this yellow square. This area specifically is located around like the continental kind of rise to the slope, in what is known as the Hillary Canyon. So Hillary Canyon is this very large CHANNEL-LEVEE system that is a pathway for this dense shelf water that is being formed in the Rouse Sea shelf, and all the sediments are coming from the continental shelf interior. And as you can see in this bottom left figure over here, the white arrows are showing how kind of goes the flow along the canyon, and it kind of touches into the 1524 area, where specifically here in the seismic profile on your left, you can see that it's this black bar showing the position of the site and how it's located in the levee of the submarine canyon. So Hillary Canyon is quite a large system. It kind of goes up to 40 kilometers wide from crest to crest and 500 kilometers deep, so it's quite large. So you can imagine kind of the size of the plume that has to be quite large also to be able to deposit some of these turbidites on this levee. So again, as I mentioned before, this plume will go down this canyon and eventually will deposit some of that sediment on the levee of the canyon, which is what we are trying to analyze here from a sedimentology, of course, point of view, to try to link these processes to oceanographic processes that happened a while ago. So the methods that we used were like already actually counting each one of these beds along the core. We counted over 3,000 of the silt beds. We took 100 samples from these beds that are shown here in the blue color. And we took some smear slides to kind of analyze the composition, which already we had the idea that were diatom rich at the bottom. But as we were like getting closer to the Pleistocene, the heterogeneous fraction was way larger. So just like a close-up in one of the cores, so you can see what we define as the turbidite beds. Of course, they were like a very sharp bottom. The top was mostly irregular. And to determine the grain size, we use a laser particle analyzer, the Master Sizer 3000. So we got all the grain size data from there. And regarding the composition, we went into analyzing several of these slides over here, and it kind of shows the how fragmented the material was, how angular it was, but in overall, it showed like a very similar grain size. Another thing that is important in that mostly of the biogenic material were, of course, diatoms. Most of them were like centric diatoms. I'm not trying to be a micropaleontologist here, but just looking at just to have an idea of what we'd have in those turbidites. So the overall occurrence in 1524 is shown here in these black lines, kind of showing the position of the different layers according to depth. And here are the samples that we took from 100 of them. And this is kind of showing the average thickness. In general, it moved from like around maybe less than a millimeter up to 2 centimeters even. But the average was around 1.5 millimeters. The grain size, the median was a very fine to medium silt between 5 and 30 microns. And the D90 reached up to maybe very fine sand, but overall, as you can see in plot A, doesn't really change too much like across the core from the Pliocene to the Pleistocene. So that's kind of give us an idea that the process was kind of the same, and even the grain size doesn't really change, even if the material, meaning diatom versus terrigenous material, changes a bit, doesn't really change the size. So that's another thing to be aware of. And next to this other plot, plot B kind of shows the concentration of the high density of the grains, so meaning that they got more terrigenous than towards the top than it was at the bottom. Again, what we saw in the smear slides also matches what we were saying before, that there's a higher concentration of diatoms at the bottom. Most of them, if not all of them, are highly fragmented. Most of them are centric diatoms, and the length kind of reaches up to 18 maximum length. Now, all these parameters, the idea was to just use them as to have an idea how the plume was and what kind of sediment we could have at the bottom of the channel by using data from the levee. So we went like kind of changing kind of the view on that process itself. So the channel sedimentation was based on the Rouse model concentration profile. This concentration kind of uses grain sizes, but enters through the idea of the Rouse number that has the settling velocity on it. So that's how we use grain size in that case. The sediment levee kind of is a function of how high the plume can get. So that's kind of where the height is. The position, in this case, the position of 1524 kind of gives us an idea how high the plume can be. And the bed thicknesses are a product of the concentration and settling velocity. So all the parameters that we found, we're using it now to kind of model this plume and have an idea of the sediment of the channel.
2 minutes.
Okay. So very quickly then, the workflow was kind of based on that. So we ran 100,000 experiments using this Lightning hypercube sampling, which I would not get into details. But then by plotting like a very broad range, then we reduce that range using the data that we actually have. And then we have 1,559 parameters combinations that kind of give us the coarse grain concentration versus the velocity of the plume. So in this plot over here, you have on the y-axis the coarse concentration grains and the velocity. And you can see already that the coarser grain needs higher velocities, which is not something that we have here, according to the data that we were able to plot. So it is mostly likely that our plume was a very, very low concentration of sediment, -1%, with velocities that went between 0.2 to 0.7 meters in the south of the channel. So this is just like one of the realizations that we got out of those 1,500 realizations, I'm sorry. And the model really shows that to have the concentration that we have in the levee, we may not have as coarse grain on the channel either, but it cannot be ruled out anyway. So just quickly getting to the takeaways, 1524 is given a great opportunity to kind of characterize these deposits, but in the context of these oceanographic processes that are happening related to Antarctic bottom water formation, and the fact that the grain size distribution is kind of the same, and the thicknesses are very consistent throughout. It suggests that it's the same process, and the frequency variations of these turbidite beds can be associated if you like plot it against ages and time, what kind of climatic events we got during the Pliocene. And in general, if we use our data into the model, we can see that we can actually model the plume based on the information that we have in the levee. And in this case, shows that the plume has to have very low velocity and very low sediment concentration. So to see what we see in 1524, and therefore the plume is not driven by sediments, but by changes in salinity and temperature, which is something that kind of confirms what we were thinking. And therefore, if that's what we have in our turbidites, meaning that the turbidites are actually being deposited by this process, and therefore we can use the turbidites as proxy for oceanographic processes, specifically the one that is recording the Antarctic bottom water formation. And just to close up, just to have an idea of how big this channel is, even though it's not really formed by sediment in itself, it's not being carved by sediment. Here we have an example of like several canyons and around the world, channel-levee systems. And if you see here, this is the Hillary Canyon, which is a massive, very large canyon. And even though it's not really carved by sediment, so I think that was one of the things that we're very surprised about. And yes, that's it. Thank you so much for listening.
Thank you very much for your presentation. So please put your questions in the question box or in the chat so everybody can answer them there. We have time for one short question, and since I see none there, I can ask one myself. So our own calibrations of the Rouse models to turbidity currents indicate that the Rouse equations tend to overestimate the concentration of the finest grain sizes in the top of the flow. And I'm wondering whether that realization could contribute to resolving this problem you have with the with predicting the silt at the top of the levees or not? That's I'm not sure this is a question that can easily be answered, but it's I'm not sure if you have an idea about that.
Yeah, this is like one of the limitations. So I'm not really the modeler, I'm just like communicating. But one of the things is that the Sultan, which he's the one doing it, he can recognize that this is a model, the Rouse model is being used most like for open channel, not really for turbidites. So that's one of the things that we were gonna like, one of the uncertainties and problems that we have. So yeah, that might be one of the constraints, but it kind of gives us a very broad and good idea for what we have right now, because so far it's kind of matching what we think it is. The fact that it's not really, sediment is not being the main driver for this.
Perfect. Okay, so very, very interesting study site for sure. Looking forward to future work.